Well, hello, this is Mr. MathWell here, and this is my Math 9, Chapter 7 review video. And so in Chapter 9, we're talking about similarity and transformations. So let's talk about what similarity is, okay? So if we have similar shapes, if shapes are similar if two shapes have the exactly the same shape, but usually different size. If we're talking about scale diagrams, we're definitely talking about different sizes. So you think about a model of a plane, a little plane model or a car model that you would put together. That is a scale representation of the original. The original is large, the model is small. And sometimes if you draw a picture in science class of an atom or something, that's a large enlargement, right? It's a large model of something that's really small. So it would have the exact same dimensions though. That's the thing. So same shape, but different size. So these two right here, this rhombus, I guess, and this rhombus, these would be similar. Now, why would they be similar? Well, we have to talk about corresponding parts in order to determine if two shapes are similar. So what are corresponding parts? Well, if you look at this side right here, the corresponding side is this one over here, okay? Now, they're the different lengths, so I'll put 2 marks here and 1 mark here. But those would be corresponding sides, okay? The side from here to here is corresponding to this side. It's the same part of the similar shape, okay, or of the scale diagram. Now, corresponding angles, let's use a different color here. Corresponding angles are the same. Like for example, they're the angles that are on the same parts of both diagrams. And what's interesting, I don't know if you can see this or not. I'm going to kind of erase. Now, actually, I'm going to just focus on these two. These two are similar shapes as well. And let's just get back to my cursor here. Now, watch this. So these are similar shapes. So obviously, the side lengths of each of these are different, right? The side lengths are different. If this was the original, this would be the model or the representation. This would be smaller, right? But what about the angles, the corresponding angles? And here's what's kind of cool about this. I'm just going to overlap these and check out the angles, okay? They're exactly the same, those two angles, aren't they? Different size, but the same shape means that corresponding angles are identical. It doesn't matter how big or small I make that. If I overlap them, the corresponding angles are the same. You see that? Okay? So when we talk about corresponding parts, right, the corresponding angles of similar shapes, corresponding angles are equal. Okay, they're always equal. And corresponding lengths are proportional. All right, so I'm going to talk about that now. And let's say that this is, these are corresponding parts. And notice that however much larger this side is to this one, it's the same proportion, okay? Or the same we call scale factor. So I'm going to just jot this down. Corresponding lengths are proportional. So there is a certain proportion that every corresponding part should be the exact same amount bigger or amount smaller, okay, as a multiplier. So here's what I'm talking about. A scale factor, okay? So a scale factor would be the ratio of the length of the scale diagram divided by the length of the original. So if I go back to this one, okay, I don't have the exact measurements, but let's say that these two sides up here, let's say that this one was times 2, okay? So this times 2 gives you this one. Well, it would have to be for this side, you'd have to times 2 as well to get this one. And this side over here times 2 to get this one, and so on, okay? It doesn't look like it's quite the scale factor there, but that's an example. You'd have to multiply the scale factor. That's what proportional means, all right? Now, if the scale factor is larger than 1, okay, it's an enlargement. So that's the scale factor is larger than 1. So as in this example, I said, well, this is about, let's say this was 2. So that's an enlargement. This scale model here is larger. This one here might be a scale factor of, oh, I don't know, let's say 0.8 or something. So 0.8. And that means we'd take this side and we would multiply by 0.8 to get the corresponding side. And that's the scale factor. So when the scale factor is less than 1, it's a reduction. Okay, so enlargements, you got it. they're larger, and reductions are smaller. Okay, so I hope you're understanding this so far. So far we've talked about like a rhombus or a a kind of a diamond shape here. You could talk about triangles, right? Pop some triangles in there. But what about shapes that are really weird or strange? Okay, so I just drew this random shape here. I copied it and I enlarged it. Now these are the exact same shape, but they're just different sizes. So that means they're similar. So watch this. If I bring this down a bit, then they're the exact same. You see that? I could overlap these now and they would map right on top of each other. But as an enlargement, the second, or the model, the representation, has to be bigger. If it was a reduction, the second one would be smaller. Okay? So what happens though? Well, how do we find a scale factor for these two? I don't see a side, right? Well, what you want to do is you can take any corresponding part. So I'm going to do this. I'm going to go from here to here. Okay? I'm just going to pick a random part of there, and I'm going to go, the corresponding part would be from here to here. And so guess what? I take a measurement of this. Let's say it's 1.1 centimeters. I take a measurement of this. Let's say that's 2.1 centimeters. And I can find my scale factor. The scale factor is the representation. So this is the model, right? We're going from here over this one to this one. So it's an enlargement. I'm going to take 2.1. I'm going to divide it by 1.1. Okay? I'll get the calculator out here. Right here. Okay, let's just put it right here, I guess. And our scale factor then is, how are we doing here? 2.1. Oh, it's not working so well here. 2.1 divided by 1.1. Okay, and that's 1.9. So our scale factor is about 1.9 if we round that. All right? That makes sense? So it's almost 2, but it's not quite 2, is it? Okay. And yeah, you can take any other corresponding length. Okay, so for example, if you wanted to check over here, this length compared to this length, or the entire length of the object, let's say, went from there to there, versus this one, would be the exact same proportion. So this length, whatever it is, times 1.9 would give you this length. All right, so that's a little bit about scale factor there. What about some properties of similar polygons? Okay, so as we said, the properties would be that we have corresponding angles are equal. Okay, so notice this angle B and angle Q, they're corresponding, and they would have to be the exact same. The same with C and R and so on. Okay, A and P. Corresponding sides are proportional. We talked about that. So I've done a little bit of work here for you on the side already. So if we take a look at this, I've got two corresponding sides. I've got 2.1 and 1.5. If I divide those, I get a number of 1.4. Now, if you didn't know if these two were similar, let's say we don't know if they're the exact same shape. We don't know about the angles, that they're all exactly the same. And so we want to check to see, well, we could just use the numbers of the lengths of the sides. So for example, I've got another pair over here. I've got 4.2 and 3.0. If you divide those, you should get the same number that you got up here. And similarly, 2.8 divided by 2.0 should be the same number. So we can confirm now, because the angles are the same, and all the sides that we've checked, well, that's all the sides, I guess, are proportional. Or did we check all of them? No, we didn't quite check all of them, I guess. Or did we? 4.2 and 3, 4.2 and 3. Yeah, I guess technically we did. So all the sides are proportional. So here we have similar polygons. Now we can use that to our advantage too, and we can find out unknown sides. Okay, no problem. But here's another one, for example, like I was saying, if you didn't know if these two were similar, they kind of look similar. So let's just see here. With the red numbers, their corresponding sides. So what's 6.7 divided by 4.7? Well, if we clear that, 6, oh, yeah, not working too well here, sorry. 6.7 divided by 4.7 is going to be equal to 1.4255. And I'm going to write lots of decimals just because I want to be accurate here. And let's check the other one, 6 divided by, and what's that one over 3.9? 9. Well, oh, Look at that. It's different. 1.538. Okay, 1.538 and so on. So what we know is that these triangles are not similar. Okay, they are not similar. So let's see if we can, I'm gonna now move this over. I'm gonna see if these angles are the same. Ooh, look at that. The angles are not quite the same. You see that? What about this one? Nope, not the same. You see that? So if I were to shrink this down, they wouldn't be able to exactly map onto each other. Look at that. They're slightly different. You see? See that? So that's how you can check, right? You check the corresponding sides and find out what the this number should be the same when you divide all of the corresponding sides. Okay. So all right, one of the questions you're going to get in your chapter 7 too is solving for an unknown side. So let's say these two diagrams are similar now. They're established that they're similar. We don't know what the scale factor is, mind you. And this is all we're given. So what you're going to do is you're going to take a look at corresponding parts again, okay? And you're going to make a ratio, a proportion. So we're going to go 6.3 divided by 4.7. And we're going to make that equal to the ratio of another set of corresponding parts that include the unknown. So we're going to have x over 3.9. So notice I've started with the second triangle and written it over a number in the first. And the second triangle, written it over a number in the first. So as long as you keep that straight, should be no problem. And of course here we multiply both sides by 3.9, which in effect brings 3.9 up to this part here, and we have x equals, this is going to be 5.23 when you do this multiplication and division, okay? So that's how you find the unknown side. And again, if you missed that part over here, same as cross multiplying and dividing, I guess. If you think about, you know, I'm going to cross multiply here. That's all we've done, taken that 3.9 and brought it up to multiply up here. Now, also another way you could do this, okay, it's really important to know this as well, is that you can do this. You can use the numbers within the question, within the same triangle, really. So you could do 6.3 over x equals 4.7 over 3.9. Okay, so that would work as well, actually. This one's going to be a little bit extra work, really, to get x by itself, because x is on the bottom, so it's going to be a little extra work, but just to show you that it can work. Okay, so cross multiplying and dividing, right? The x is going to go up there, 4.7 is going to go down here, 3.9 is going to go up there. Okay, so you're going to have 3.9 times 6.3, right? And you're going to have x is going to be on top over here, and the 4.7 is going to be down over here. And that's exactly the same thing that we had before in the previous. So again, there's two different ways you could do that. You could set it up either way, as long as you're consistent, you know, with setting up your proportion. You make sure that, you know, the corresponding sides seem to fit in the corresponding parts of the equation. Okay. All right. So let's get into the next part here, which is symmetry. Okay, chapter 7 also deals with symmetry. Now there's two main types of symmetry. That's line symmetry and rotational. Line symmetry is pretty easy. You draw a straight line through an image or a figure, and if the left side and the right side, or the top and the bottom, or the one side of the line is exactly a mirror image of the other side, they're exactly the same, they can fold over that line and map onto each other, like my hands right here, okay? There's line symmetry right in between the tips of my pinkies, because if I fold my hands over, they exactly map onto each other. So this figure right here would have line symmetry, okay? A single hand would not have line symmetry. It would not, because there's no line that I can draw where it would exactly map onto the other. See, the pinky and the thumb are different. So if I drew a line right here, you might think, oh, there's a line of symmetry right there. There's 5 digits, and, well, this one and this one are different. These two might be considered the same, okay, except for the ring, I guess. But the pinky and the thumb definitely aren't. So you have to be careful about line symmetry. So technically it says this: a shape has line symmetry when a line divides the shape into two congruent parts, so that the one part is the image, remember, the mirror image of the other, after reflection, a reflection in that line. So here's a question from your review, in your textbook. Which of these traffic signs have line symmetry? So I take a look at A, and if you drew a line right here like this, is that a line of symmetry? Well, if you folded it over, you'd have an arrow on one side, and there's no matching arrow on this side. So that's no good. Whoa. But what about if we drew a line this way? I don't know, maybe you see this already. But if we drew it right through this point, right through the very middle, and now if we folded the top over onto the bottom, it would be the exact same. So there's a line symmetry. The stop sign, okay? If we include the letters, there's no lines of symmetry because the letters wouldn't map onto each other in any way. But if we ignore, I'm going to fill this in now. If we ignore the stop part and just look at the shape, well, I guess you would have line symmetry here, and you would have line symmetry here. Are you getting me? And here, and here. And what about at the points? I'm kind of looking at the points here, at the corners, and saying, what about this? Would this work? Well, we have this one matches with that. This one matches with that. This one matches with this one, and this one matches with this one. So it looks like you have line symmetry through these corners as well. So there's lots of line symmetries if you do not include the word stop, but if you do, there would be none. Okay, and this one down here, looks like we have a line here, that, and a line right here. Okay, this one, what about something like this? Well, close, but again, you have train tracks over here matching with a road over here, so those wouldn't fold onto each other identically. So the red one is not a line of symmetry. Okay, so two lines of symmetry here, one here, many over here. And what about this one? Well, the yield sign, looks like we have one there. That's a bad line, but we have one here. And looks like we have one here, right? And looks like we have one there. So we have three lines of symmetry for that one. Okay, so that's line symmetry. It's pretty straightforward. Draw a line. Rotational symmetry. Okay, this is the tough one. So rotational symmetry, literally, if you take a shape and you can spin it, and if, when you're spinning it, you get to the original position before you get 360 degrees around, then it has rotational symmetry. Okay? Now, there's a little, I'm going to show you just a little YouTube video clip here. So kudos, just a credit out to MKU2 Tube, just for this little clip. And I'm just going to play this. And so if we look at this shape right here, watch how it rotates and how it maps onto itself before it gets all the way around. You see? Boom. You see? Now it's identically, it's right on itself. So what did we do there? How far did that move? Well, let me just clip this. I'm going to clip this and bring it into my notes so I can monkey with it a bit. All right. So what we did was, this was the center, the point of rotation. Okay. So there's usually there's always a point of rotation. It could be in the center, or it could be a corner, or it could be the origin on the coordinate plane. But what we did was we took this point. If I follow this point right here, it went around all the way to here, and that is a rotation of 90 degrees. Okay. Now, if we kept going, it would map onto itself again here and here, and then before it got back to its original position. So that's 1, 2, 3, 4 mappings within one full rotation. You see that? Okay, so let's take a look at what this says from your textbook. It says a shape has rotational symmetry when it coincides with itself after a rotation that is less than 360. Okay, now they're specifically talking about the center. So on a shape on itself has to rotate about the center. There is you can rotate shapes about another point, but for an actual shape to have rotational symmetry, it does need to spin on its center. So specifically, we're dealing with this. You'll have to rotate things when you move on with math around another point, but this one, I guess, is dealing specifically with the center. That's good. That's a little bit easier. The number of times the shape coincides with itself is the order of rotation. So this one would coincide with itself 1, 2, 3, and then 4, right? So that's an order of rotation of 4. And finally, the angle of rotation, okay, is 360 divided by the order. And of course, we said here that the angle of rotation was 90 for this one. And that's 360 divided by 4. Okay, and so we'll conclude with this question from your review in your textbook here. And the order of rotational symmetry of each shape, what is it and how do you know? Okay, well, this, if we take a look at where the center would be here, oops, don't want to do that. I got to change my mouse settings here. New computer. Okay, so if the center's here, and guess what? This is going to, let's start with this one, I guess, okay? So it's going to rotate through, and when it gets to this point, because this is very, symmetrical, then it's going to map onto itself when we get here. It's also going to map onto itself when we get to this point, and then when we get back to the middle. So that's 1, 2, 3 points, right? 3 times. So the order of rotational symmetry here is 3. What's the angle? The angle here, well, that would be the angle between this point and the center and this point. And that's going to be 360 divided by 3, or 120 degrees, okay? Awesome. Okay, so this one, let's say we start at this point here. Well, if we rotate all the way around to there, you see, this is going to go to there. So that's going to map onto itself 1 time, and then you count the original position as well, or the final position, whichever one. But this has 2. So its order of rotational symmetry is 2 for this one. Okay, down here, again, if we start here, and we go 1, 2, 3, 4, 5, and 6. So this has a rotational order of 6. Okay, and then you do the same sort of thing because these are all very, very symmetrical. As soon as we hit the next kind of point that's identical, all the other points are going to move in the same way too. So we've got 1, 2, 3, 4, 5, 6, 7, and 8. So this is an order of 8. So rotational symmetry is when you spin the shape around its center, how many times does it map upon itself? And and of course the angle of rotation, the order of rotation, something you need to know as well. So just in review, as we move back, lines of symmetry here. You draw a line through a shape, and can it fold over exactly onto itself? And some shapes have many lines of symmetry. Okay, similar shapes have exactly the same angles. The corresponding angles are identical, and the corresponding sides are always proportional. So you divide the corresponding sides, and you always should get the same number. That's if they're similar. Okay, scale factor. Well, again, working back from the beginning where we kind of started with the scale factor, it is simply the result of dividing 2 corresponding parts of similar figures. And corresponding parts could be the line segments, the edges, or they could be any corresponding parts of some irregular figure like we did here. Okay? Where scale factor is greater than 1, that's an enlargement. If the scale factor is less than 1, and I should maybe note here that it's between 0 and 1 really. So it's between 0 and 1. It's a decimal between 0 and 1. A negative 1, we're not going to get into that. We're not going to get into negatives. But we're just going to talk about between 0 and 1. That's what this means, less than 1. And that's a reduction. Okay? So just remember that angles are the same and sides are proportional. So remember this graphic here. If we bring a similar shape onto the other one, the angles should be exactly the same. Okay? So there's your review for Chapter 7. Similarity and transformations.